Okay, let's get started. So I think this is the last presentation that we're going to be doing on induction machines. And we spent a lot of time on them, right? Because they are really important to a lot of what we do in this world, particularly from an industrial experience. But we also talked about those restaurants, right? When they have those big not heating systems, but ventilation fans, or all the washing machines, right? That they have to run, the dishwashers where they have to run at really high pressures at really hot temperatures. It makes sense to use three-phase motors, and they're industrial, right? They run, I don't know. I've never worked. Well, I did work as a dishwasher once many years ago, but we would probably do, when we were busy, a load a minute or something like that. So they probably get a lot of use, and it's a lot of starting and stopping, which, as we saw in lab this week, you can hear the motor straining a little bit because of those blocked rotor conditions. And then over time, it gets better. So motors that are operated for continuous duty have a little less beef to them, if you will, than ones that are starting and stopping all the time. Like compressor motors, when they start and stop, especially if it's cycled on and off a lot, that's particularly hard for the motor. Most compressors, right, aren't just a standard compressor where it just compresses air. You always have some sort of a tank where you can maintain a certain pressure. And if you've ever been to an automotive place or whatever like that, they have, it looks like they're 100 or 200 gallon tanks to be able to store that air capacity. And again, that's really for two reasons. The first is to go ahead and make sure that the compressor has enough air, right? So if you want 100 PSI air, it's going to stay relatively stable. But then also it keeps it so that the compressor doesn't constantly have to start, stop, start, stop, start, stop. And one of the things kind of interesting about a compressor, if you've ever run a compressor, you'll actually hear when it stops. If you listen, you'll hear like a lot of air going out. Anybody know why that is? Why is a compressor, when it shuts off, you hear like a quick release of air? Anybody know why? So if the compressor is doing its thing and compressing air, right, inside the cylinders are 150, 200 PSI air, correct? If you start the motor under load, meaning you've got 150 to 200 PSI air already in there and you're trying to compress it, that's really hard for the motor to start. It can, but it takes a long time for it to start. So every air compressor that I'm aware of, the very first thing it does is when it shuts down, it releases all the air that's in the cylinder. So you basically have like a check valve so that the air goes into the tank and not back out of the tank. And then you can you can release the air for 3 seconds, whatever. And then when you start the compressor up, there's essentially no load, so it can start a lot easier. So that's when we come into the concept of locked rotor or inrush current. We saw this a little bit in lab. When we were under locked rotor conditions, you can pull a fair amount of current. And it looks just like, excuse me, an RL circuit, because remember our equivalent circuit, that resistor R2 over S, well, when it's fully slipped, it just becomes R2, right? So you have an inductor in series with a resistor, but you're not really putting any output power because there's no speed. So the highest amount of current that you should ever draw for your motor is when you start it. And if you actually look at the protection characteristics for a motor, they actually are designed so that under short time frames, 5, maybe 10 seconds or less, you actually can start your motor. You can pull a lot of current in, but after 5 or 10 seconds, then you should be at your normal full load amps. So you don't want to indefinitely allow that large amount of current, unless, again, we talked about the the fire pump, right, when you had that application. So you actually have to design starters to actually go ahead and do that. And so that's one of the things that looks at it. Here is our inrush current when we look at it from a perspective of AC, but in real time, not steady state. And you can see we have this, whoops, where's my pen? There it is. Over here is my transient condition, because that inductor might have had some magnetic field stored in it in some way, right? The magnets may have been magnetized. And so you're going to store some energy in its magnetic field. And so what happens with any inductor is it hates that instantaneous change in current. So if you're trying to close on the sine wave that is not necessarily zero, it's going to provide a DC offset. It's going to try to oppose any change to maintain that. And so you're going to kick a little bit of DC, and then that dies out very quickly. The time constant on an induction machine is very, very low. So it dies out after maybe 2 cycles, and then you have steady state until, again, you reach operating speed. Now, that can take 1 to 2 seconds. It could take up to 60 seconds when we talked about centrifugal fans and sort of the speed there. And so that's perfectly fine. It's acceptable that you see operation like this. You just don't want to sustain it for a long period of time. Let me get this up on the side. This kind of shows you a little bit of our equivalent circuit, but we want to include the transient, the decaying exponential part. So here is our RMS value. And then to put that into a time domain varying one, we have our sine of omega t. Theta z is the impedance of the machine. So we have a voltage that's at 0. So our current is going to be lagging current, right? So we have a phase shift associated with it. And this RMS value is here. And then why do we multiply by the square root of 2? Because when we represent things in the sine wave, we have to go to peak values, right? RMS, we had to divide by the square root of 2 to get those values correct. So we need that back in there to represent this as a time varying quantity. So let's look at our transient value. Remember, it depends totally on when you close the switch. And the easiest way to do a first order time constant is some magnitude. We'll call it capital A here. And then our decaying exponential, e to the minus RL over t. Our real part of our circuit is some input impedance, right? That's the Zn of the machine. And that's looking at the total machine times the cosine of Z. So we're taking the real part of it. The inductor is XL, which is the imaginary part of Z. So it's Zn sine of theta Z. And we want to divide that by omega because this is L, right? When we talk about transients, we don't use X sub L, we use L. So we need to make sure that we convert that to an actual Henry's value, right? Because XL is in ohms, L has to be in Henry's. And so again, we're going to just have to determine what the coefficient is at the initial condition. So we don't always know what that is. We can assume a peak value, but for the most part, we'll just kind of leave that as an unknown. And then writing our impedance as a complex number, we have that value. So we combine those two. And here is our AC part. Here is our DC part. So if we could, we would see very quickly, right about here, that's the DC decaying exponential. So we have a sine wave. This is our sine wave part, plus that's our DC offset. Okay, it's decaying, but it is a DC offset because we're discharging that magnetic field, which is trying to oppose any change there. So how do you show that? How do you represent that? That's a lot of information if we're looking at things from a transient's perspective. But most of us, if we're designing systems to integrate engineers, we can look at a nameplate. And I have a figure here. Let's go ahead, and I just brought this one up before class. Let's take a look at a newer motor. This is Baldor. They make all kinds of different motors. This is severe duty. Pretty fancy, right? I don't know what that means, but we'll see if we can figure it out. Catalog number. So this is the standard. NEMA MG1 has standards for what you're supposed to put on a nameplate. And catalog number, again, that's just the manufacturer's catalog number. Then you have enclosure. Anybody know what the enclosure is of a motor? The enclosure of a motor depends on where it's going to be located. So the best application you can use is called an ODP, open enclosure, but it's drip proof, meaning you can see the windings, like one in our lab, or for those of you doing it online, you can look inside the windings. But there's a case on top of it. Why? Because if water drips on it, it's not going to get into the windings, right? It's going to hit the casing and then hopefully just roll off and not have cause us any problems. Why would you think that that's the best design application in terms of cost and efficiency? Exactly. You open it up right on each end, you can move a lot of air through there. So you can have a fan pull all kinds of air to help keep it cool. Okay. So open drip proof is preferred for that primary reason. The problem is that if you get a fan and it's blowing air, what's in the air? A lot of junk, right? Yeah. So over time, those windings will get covered with dust and soot and whatever else is in the ambient environment. So if it's like in a somewhat clean factory, no big deal, right? You can get somebody with a vacuum cleaner or compressed air, or even better yet, you can get the motors rewound. So you send it to like AC Electric in Bangor, and they'll pull the shaft out on it, and then they'll dip the oven in this chemical process. Actually, what they do for those, typically what they do is they take the whole motor and then they just power wash it. You think that's crazy, right? Why would you power wash a motor? Because you're spraying water in the windings. Well, trying to clean it. And if you have bad insulation, it might be okay at a motor manufacturing rewind facility to find that there's bad winding insulation there. So they power wash it and then they put it in an oven, bake it to get all the moisture out of there. And that like gets it 97% of the way clean. If you want to rewind it and go the extra step, then they got to pull it and they got to change all the windings, et cetera, et cetera. But the first thing you do, you bring it into those facilities and you just power wash it, and that works perfectly fine. So as long as you can dry it appropriately, and that's the hard part, right? Not everybody's got an oven that can handle, something that might weigh 4,000 pounds and is the size of your desk, right? And it's going to be maintained at that pressure. I mean, at that temperature for however long. There's rules of thumbs because inside the insulation, right, it's hard to get to, but the water can eventually track its way in there. And so what you do is you just keep it heated at, I don't know, 200 degrees, well above the dew point. And as the water heats up, eventually it flashes to, it flashes the steam essentially, or not steam, but it basically condenses, or not condenses, it evaporates. And then you can get all the water out of there. And so that's one of the things you do is you dry the oven by baking it, running at a pretty high temperature to do that. So this is not open drip proof. This is TEFC, which stands for totally enclosed fan cool. So this motor, all internals are completely sealed from the outside. So there is a fan on this, but it has heat sinks on the perimeter of the motor that you can get some heating to hopefully go in those locations. It's not a very good, way to remove the heat because again, it's not oil where you can direct it. You're just relying on these fins to help extract some of the heat across it. So its efficiency is going to suffer, and it's going to have to be oversized to make it work. The spec, again, don't have to worry about that. I don't know about the CC. Frame size is very important. Again, you go to NEMA MG1 and you can find some standard frame sizes. The reason being is because if you buy a 10 horsepower motor, you might need to replace that motor with another 10 horsepower motor. If you have the same frame size, that motor will exactly mate up with your existing application. The foot or the feet for where the motor is, where the bolt holes are, the height of the shaft, there's a keyway in the shaft that you can couple. All that stuff is standardized and makes it really, really simple to swap out some motors. So really useful. Horsepower, right? That's an output horsepower, not an input. So that tells our mechanical friends what that is. Class F, which is the insulation class. So in industrial applications, the class F just tells you the amount of temperature over an ambient that the insulation will survive. So a class F, I think it's 40 degrees C over ambient, which an ambient might be 40 degrees C. So the insulation won't break down as long as it stays below 80 degrees Celsius inside, or the hot spot of the windings. You can get higher one, and one of the way to make sure that you get a better quality motor, and I've done this in the past, is if you want a better quality motor, you want it to run cooler than what it's rated for. So you say, I want a motor design to operate with a class B temperature rise. So maybe that's 20 degrees C, but the insulation is capable of a class F rise. So it actually has higher capability than based on what the design of the motor is. And so you get a little bit better quality motor. 60 Hertz. This is the NEMA design. Remember the A, B, C, D for the different operating characteristics. This would be a design A, which is kind of atypical. Usually it's B, but A is perfectly available. 1180 is the RPM. I think that's 1180. Can you tell me how many poles this machine has just by looking at that? Remember, it can't operate at synchronous speed, but it likes to operate as close to synchronous speed as possible. So what would that synchronous speed most likely be? 60 hertz, 1200 RPM, right? So this would be a 6-pole machine, most likely. Max RPM, I think that says 1300, but it might say 1200. But anyway, that just has nothing to do. That means something is externally pushing it. It won't run at that speed. Three-phase, this is the thing that tells us the inrush code. This is a code, and we'll look at that more in a minute, but it tells us how many kVA per horsepower you need to start the application. So it's just a way of calculating the approximate amount of inrush. And then it's dual rated, which a lot of motors are. 230, 460 works really well. So this is only at 20 horsepower, but look at the weight, 437 pounds. So remember what I said, right? Being able to put that in your oven, something like this. And it's not big. It's not physically that big. It's just got a lot of iron and metal in it. So it's going to be a pretty heavy unit. Then it tells you at full load amps, it draws 54 at 230 and 27 at 460. Its service factor, again, is its nameplate is rated at 20 horsepower, but it means it can run at 1.15, the service factor, and still be able to do continuous operation. So it actually can go 20 horsepower times 1.15. Our power factor, if you remember in lab yesterday, we had 73%. This one is 77%, which is pretty typical. Induction machines typically have a pretty poor power factor. So you oftentimes have to correct those with capacitors. But 75 to 80% is not that atypical. Efficiency, though, 92%. Pretty darn good, right? You think about it, this is not even a premium efficiency. It's a severe duty, but we can get 94, 95 pretty easily. And then this one has nothing to do with the motor, other than the fact that anybody know what Class 1 Div 2 means? It's in the National Electric Code. It has to do with hazardous area if it's flammable materials. You have a classification and a division. So it tells you the type of equipment that you are required to operate in there. Because obviously you don't want a motor that has arcs and sparks in a place that natural gas is all over the place. It's going to cause an explosion. So any place that it could be explosive, like if you're in a propane facility, or if you're coal, if you get a bunch of coal, or what about a paint booth? If you're in a paint booth, right, there's a lot of fumes. I remember doing something, I have an apartment building and I had to do a lot of painting over some old plaster walls. And what I read is to use oil-based primer to make it work. And so I used oil-based primer and I had one of these little detectors in my basement for flammable gases. And that thing started going off as the paint was evaporating. It was enough. So it could have been that was flammable enough. That was just paint, oil-based paint drying. That could have been explosive. So paint booths are an issue. Another place that is kind of less obvious, but if you have a lot of ammonia, if ammonia can concentrate, that can be explosive. And so there's some real issues with doing that. So this would be an application for Class 1 Div 2. This one also has space heaters. Why would you have space heaters? If the motor doesn't run for a while, it's sitting there at ambient temperature, 68 degrees. The dew point outside is, I don't know, 46, 47, whatever. You can get some condensation on your windings. And once that water is in there, it is tough to get it out. So we talked about baking the oven, but in more important motors, you actually can put space heaters that when the motor shut down, you energize it. It brings the motor windings up to like 160, 180 degrees, and you can't get any condensation in those because those windings are too hot. So space heaters, you see those for a lot of electrical equipment, generators, motors, breakers. Sometimes you want to keep the cabinets warm because the gas that's in there could get bad. So you keep your cabinets at a reasonable temperature above ambient, and then you don't have to worry about corrosion or electrical insulation because of the water. I think that's all the important stuff there, but let's go back to that kVA code. So this over here. So the motor on the previous one, it's NEMA Design B, which again, just tells me the operating characteristics. It has 150 horsepower at 460, 60 hertz. It has 163 amps and a nominal efficiency 96.2%. Let's go back up to that. So this is an energy efficient reliance motor, right? So pretty good, 96%. Now in this one, it has a kVA code G. Tells me I need so many kVA per horsepower to start this winding. Here's the figure that you need, okay? So in the example that we had here, that was a code H. So if we were doing that, it takes 6.3 to 7.1 kVA per horsepower to start that motor up. How do we use it? Well, for this one, it's code G. So we take our kVA per horsepower, whatever that range is. Then we multiply it by the number of horsepower. And then we multiply that by 1,000, right, to go from kVA to VA. And then we solve for I line. So in the application that we saw that 150 horsepower, even though it pulls 163 amps at full load, the lower limit for where it starts, it pulls over 1,000 amps, 1,054 amps. When it starts, that's a low range. At the high range, it's almost 1,200 amps. And that's perfectly fine. That's what the motor requires to operate efficiently and effectively, to at least get started. Once it's started, then it's different. Transformers also operate like this. Any consistency between transformers and motors, induction motors? We said an induction motor is a rotating transformer, right? So you have the same issues with transformers. They have an inrush current, just like induction motors do. But there's no usual kVA. There's just some standard ratings that we use. So we got to design our protection system for these values. So here's our lock rotor range, and here is our full load current rating of the motor. All right. So I don't have a ton of stuff today because we have to talk about our next test. I haven't written it yet, but I got to. Let's look at the syllabus. Because we have to have an exam next week, right? We're not allowed to have exams in the last week of classes. So if we look at our dates, right, and it would be the lab, our exam would be a week from yesterday because today's tax day. Everybody hooting and hollering because you had to pay your taxes by now. Actually, it's by midnight tonight, I think, right? Or maybe it's midnight last night. I'm not sure. What's that?
I can't remember.
It's either one. Anyway, you have a choice. You can do an exam on Monday from 8 to 11, get 3 hours. But I understand that that's 8 o'clock on a Monday, which is not the best time. The other option, and it seemed to be at work okay last time, is we can do Tuesday during class or Thursday during class. It's your choice. I'll put a poll up for the people in TV land. Oh, there's a chat here. Thanks, Reed. Sorry, I didn't. Next time, if you see something, just let me know that I need to take a look at the chat. So let's edit. So it'll be, let me add a choice. $11, not 100. All right, let's launch this. All right, for those of you in TV land, or if you want to have it even on your phone, it's your choice. I just need to get what people's preferences are for the next exam. And then for those of you here, when would you like to have the exam? Who votes for Monday? Who votes for Tuesday? Who votes for Thursday? Okay. That is easy. So it was unanimous in class that they wanted on Thursday, and it's not unanimous here, but it's pretty consistent with the results that we have here. So we'll do our next exam, not exam 2, but exam 3. We'll do it Thursday during class. So the only thing is, let's change this. And let me launch the poll again. So edit. Edit it. Okay, I guess I have to do this one because I launched it already. So how can I edit? Oh, there we go. So it'll be either this Thursday, which is the 15th, or Tuesday. No, this is the 17th, or Tuesday, the 22nd. One load away. All right, go ahead and have your preference for when you want the exam 3 review. And over here, who wants the exam on this Thursday, review on this Thursday? Who wants it on Tuesday? So maybe I wasn't clear. The reason why we would do it on Tuesday is it's closer to the exam, so it gives you a chance to have studied the material a little bit. So you actually might have get a little more out of the exam review. Whereas if we do it on Thursday, you've only got, a couple days to study. So right now it's Tuesday on here. What about TV Land? How about this coming Thursday? This Thursday?
Yeah, if we had on the review on Tuesday.
I would probably start off and doing a little bit of power electronics. Yeah, but that won't be on the test. Okay, Tuesday. Who wants next Tuesday? We get to raise your hand. How about Thursday? Okay, so it looks like we'll do an exam review on Tuesday. And which is good, gives me a little time to get it up there. And then we'll also do the exam on Thursday. It's going to focus on induction motors, right? Asynchronous machines. But everything that we've done to this point is applicable. Let me just double check one thing to make sure that I don't have any more induction motor material. I think that that's it. Oh, no, wait a minute. I have, let's see what this is. No, that's not it. What's going on? Pages 81 to 94. That doesn't look right. Yeah, I think that that's it. So what we'll be doing in the next class is we're doing a little bit of power electronics. And why power electronics? Because that's the future, right? Speed control. So we'll talk a tiny bit about IGBTs and all that stuff, but we won't have a lot of time because we'll have one class, then exam review, then exam, then we go over the exam, and then you have one last class for the semester, which would be the final review. So we basically only have one class to do new material. Yes, sir.
Do we still have one more lab? Not this week, but another lab?
No. So next week, because you have an exam, I'll give you that lab period to go ahead and study for the exam. And then the following week, we might do a general study session. I guess we'll just kind of see where everybody's at for the final. So yeah. But that's all I had. Short one today. Any questions? I haven't done it yet. I got to do it because I got to figure out what's going to be on the test. So, I can give you a review guide, but I can't give you the questions. So I'll try to work on that today and get it done. What's that?
When did we drop off to,
That was
Yeah.
synchronous motors.
so. Some. Smaller things from the.
No, we're not going to be focusing on any synchronous. It's all
Well, some of
induction.
The calculations for the small things that you might need for it. Just that's kind of like the last one we had.
Yeah, so being able to do three-phase power calculations, doing AC circuit analysis, all those things are really useful. And if you remember, when we did our plots, remember in MATLAB, we did the plots? We actually did, and I showed this in lab, we actually can actually do a plot and come up with a torque versus speed characteristics. And we all did that by the equivalent circuit. So the equivalent circuit, we did all AC circuit analysis. We did mesh analysis, remember? To go ahead and do that. So we did power calculations, P in, P out. We did conversions between power and torque. Understanding the concept of synchronous speed and rotational or mechanical speed. That's the big thing. So if you really want to understand induction motors, I would spend my time studying what's going on here. How is there a difference different in speed? It's because mechanical speed can't be the same as synchronous speed. And we even saw that in lab, not only with the induction motor that we just did this past week, but even previous week when we did synchronous motors. Remember when we had our field circuit open, we had the switch in the open position. It ran at 1750 RPM, not at 1800 RPM. It's only when we flipped the switch is when it ran at 1800 RPM. That was a synchronous motor. But prior to closing the switch, it is operating just like an induction motor. And that's one of the ways that you can start synchronous motors. But that material is on previous. So we won't really focus on synchronous stuff, other than what is synchronous speed.
So more of the induction motor.
Yep. But doing those power diagrams, right, the power flow diagrams, and we don't really talk about induction generators because they're really not used that much other than wind turbines. You hardly ever will come across an induction generator. Like I said, the only time I've ever seen them being done is for wind turbines. Everything else is always synchronous. So we don't really spend any time. Synchronous motors, we covered a little bit because we're starting to see more of those for voltage support. And I worked on a project in Huckins Hill, New Hampshire. This is a few years ago, where they put a 50 MVA synchronous condenser, which is a synchronous motor. And its whole purpose is to run unloaded until you need voltage support on the grid. And then you can go ahead and monkey with the excitation system to give you the voltages you need. All right. Anything else? Okay. Have a great day. See some of your senior projects. Otherwise, I will see you around. Take care, everyone.